Good morning. Today I'll discuss on axial flow turbine. The contents of the lectures are axial flow turbine, introduction, fish line design and analysis, blade loading capacity, pressure distribution around a turbine blade. Let's begin with the introduction. A gas turbine unit for power generation or a turbojet engine for production of thrust primarily consists of a compressor, combustion chamber, and a turbine. Thus, the high pressure and temperature gas is expanded through the turbine to produce power. Like compressors, turbines can be classified as radial flow turbine, axial flow, and the mixed flow machines. Indeed, the choice of the turbine or the types of turbine used would depend on the application. Furthermore, it should be noted that the axial flow turbine is capable of handling comparably higher mass flow rate. However, pressure ratio per stage is lower than the radial flow machines. However, multi-staging is very easier here as compared to the radial flow turbine. The efficiency of a well-designed turbine is generally higher than that of a compressor. I've explained here why the efficiency of a turbine is often more than that of a compressor. Please note that the pressure drop within the turbine blade passage keeps the boundary layer well behaved, and the flow separations can be avoided here. However, the flow often separates within the compressor passage because of adverse pressure gradients. Furthermore, due to favorable pressure gradients in a turbine flow passage, much more turning of flow is achievable without danger of flow separation. This means much more work and considerably high pressure ratio per stage is possible. Offsetting this advantage, much more critical is the stress problem, since the turbine rotor is exposed to high gas temperature. Furthermore, the blade shape here is often more dependent on the stress and cooling considerations than the aerodynamic considerations. I'll explain here the two-dimensional pitch line design and analysis. An axial turbine stage consists of a row of stationary blades called the nozzle or stator, followed by a row of rotating blades called the rotor. A figure has been presented in the next slides. The large pressure drop per stage occurs due to rapid expansion of gases to the nozzle and the rotor blades. For a high pressure turbine, which is often designated by HPT, the hub to tip ratio is quite high. That is, the blade height is small here. Thus, the radial variation of velocity and pressure may be neglected in a HPT, and the performance of a turbine stage is often evaluated from the performance of the blading at the mean radial section, which is called two-dimensional pitch line design. It should be noted that for a low pressure turbine, which is designated as LPT, the hub to tip ratio is low, resulting in a considerable large blade height and a large twist of blades. Thus, the two-dimensional pitch line design is not valid in case of LPT. I have presented here the schematic of a gas turbine stage where the stationary blades are indicated by nozzle followed by a rotating plate which I have designated as rotor. Now rotor is connected to the rotating disc, so I have shown here the hub radius are hub and tip radius are tip. I have also indicated the annulus area by A and indicated three sections as 1, 2, 3, where 1 represents the flow conditions before entry to the nozzle or stator ring. 2 represents the flow conditions from exit of the nozzle or entry to the rotor, and similarly the condition 3 indicates the exit from the rotor. Furthermore, as I've stated earlier, the absolute velocity is denoted here by C, and the relative velocity would be as W. In two-dimensional approach, the flow velocity will have two components. One is axial component and other is peripheral component, denoted by the subscripts Z and theta respectively. Furthermore, the absolute angle is represented by alpha and the relative angle would be represented by beta. Here, I have also stated that condition 1 indicates the inlet to the nozzle, 2 in between the nozzle and the rotor, entry to the rotor, and 3 indicates exits from the rotor. Here I have indicated the velocity triangle through a stage of a turbine blade, particularly the gas turbine blade. Now note, as before, this is the nozzle followed by the rotor, and I have indicated here a dotted line which is the mean circumferential section. Now if that section is stretched on a plane of paper, I'll get the blade profiles, and now let C1 be the velocity, absolute velocity at inlet to the nozzle that makes an angle alpha 1 with the x-axis. X-axis is the axial directions and theta is the tangential directions. Now the C1, that is inlet flow to the nozzle, will be accelerated as the flow will pass to the nozzle. The C2 will be the absolute velocity at the station 2, which is also NT to the rotor. Thus, at the station 2, I have indicated the velocity triangle as W2 plus U is equal to C2. Now, W2 is the relative velocity which enters to the rotating blade. That makes an angle beta 2 with the z-axis, and C2 makes an angle alpha 2 with the z-axis. Now please note that superpositions of W2 and U will give you the C2. Now here C2 is much higher than the C1 because of acceleration of flow within the nozzle. Now W2, which is the relative velocity that's entering to the rotor. Now pressure drops through the rotor may occur also, and therefore I have shown here W3 is higher than W2. So W3 makes an angle beta 3 with the z-axis. Thus W, here I have indicated W3 plus vectorial additions of U3 would give you C3, and beta 3 is the angle that W3 makes with the z-axis. Similarly, alpha 3 is the angle that C3 makes with the z-axis. Now here obviously I have considered U2 is equal to U3 is equal to U. So this is the velocity triangle for a compressor stage, and you have, hope you have appreciated the different relative and absolute velocity. Please note that after drawing the velocity triangle through a stage, I'll find the expression for work transfer in a turbine stage, discuss about the work done factor and the blade loading capacity. Now here I like to discuss that for turbomachinery we use some sign convention. What are the sign convention associated here? That any velocity that we measure in the direction of rotation is considered as positive, while in the opposite direction of rotation is considered as negative. Suppose, as an example, you may measure C theta. In the direction of rotation, I'll consider C theta as positive, and if C theta be in the opposite direction of rotation, it will be considered as negative, and so as to W theta. Please note that I have indicated here the velocity triangle at inlet to the rotor and exit from the rotor of a turbine stage. Now, as per the sign convention, C theta 2, which will be in the direction of U2, would be treated here as positive, while W theta 2 being the opposite direction of U2 would be negative for a turbine. Similarly, at the exit of the rotor, C theta 3 would be positive and W theta 3 would be negative. Considering this, I have stated here that the nozzle accelerates the flow, imparting an increased tangential component of velocity. Thus, there will be change in tangential momentum of fluid leading to torque on the rotor in the direction of motions. This means the fluid does work on the rotor, applying the angular momentum. Thus, the power output would be P is equal to m dot u2 into c theta 2 minus u3 into c theta 3. C theta is the projection of C in the tangential direction. In an axial turbine, we can assume u2, that is blade speed, must be equal to u3 equal to u. So thus, if we consider this u2 approximately equal to u3, that be designated as u, the work output per unit mass flow rate is given by Wt is equal to u into c theta 2 minus c theta 3. I have presented here the combined velocity triangle of a turbine stage. That is, velocity triangle at inlet to the rotor and the exit from the rotor are superimposed here. Please note that W2, U and C2 represents the inlet velocity triangle, while W3, U and C3 indicates the exit velocity triangle. I have also presented here the relative and absolute angle of both the triangles. Furthermore, please note that C theta 2 and C theta 3 being in the direction of rotation are treated here as positive. Del C theta is the difference between C theta 2 and C theta 3. Cz is the axial component of C in the direction of Z, and here the axial velocity component Cz is treated almost constant as the flow passes through the stage. After discussion of this, I have defined here W2, that is work output of a stage, is equal to Cp into T01 minus T03, where T01 is equal to total temperature at entry to the nozzle, and T03 be the total temperature at exit of the rotor. That is, the total temperature at the inlet of stage and total temperature at exit of the stage. So thereby, Wt must be equal to stage enthalpy drop in the stage. From this equation, I can write, or I can define the temperature drop in a stage del T0 as T01 minus T03, that must be equal to T02 minus T03, as there will be no work output from the nozzle. So total temperature remains constant. So that is why T01 here must be equal to T02. So I have defined the temperature drop in a stage as T02 minus T03. Now we can find out the stage work as del T0 by T01 is equal to Wt divided by Cp into T01, that is equal to U into C theta 2 minus C theta 3 divided by Cp into T01. Thus this equation 2 gives us non-directional temperature drop in a stage. Now using the combined velocity triangle as I have illustrated earlier, I can get the following relation as U is equal to C theta 2 minus W theta 2. Note that W theta 2 is negative here. Thus, From inlet velocity triangle I can get U is equal to Cz into tan alpha 2 minus tan beta 2. Thus U over Cz is equal to tan alpha 2 minus tan beta 2. Similarly, from the exit velocity triangle, I can write U by Cz is equal to tan alpha 3 minus tan beta 3. Now, the Euler equation yields as Wt is equal to U into C theta 2 minus C theta 3. Thus, W2 would be equal to U into Cz into tan alpha 2 minus tan alpha 3. This relation I will get by putting the expression of C theta 2 and C theta 3. Now, if I use this relation as I stated here, U by Cz in terms of alpha and beta, I can write Wt is equal to U into Cz into tan beta 2 minus tan beta 3. This is equation number 3. Now this equation 3 gives the expression for Wt, that is turbine work output, in terms of flow angles associated with the rotor blade. Note that the work done factor in case of an axial turbine is unnecessary. This is because of the growth of boundary layer along the annulus passage is much less in an accelerating flow than when the flow is encountered with an adverse pressure gradient for a compressor. Now, the work capacity of a turbine stage can be defined as Xi is equal to Cp into delta 0 divided by U square. That's equal to C theta 2 minus C theta 3 divided by U. Hence, using the velocity triangle, I can write Xi is equal to Cz by U within bracket tan beta 2 minus tan beta 3. This I have given the equation number 4. Or I can write Xi is equal to phi into tan beta 2 minus tan beta 3, equation 5. Xi is a dimensionless parameter which is called the blade loading capacity or the temperature drop coefficient. In gas turbine design, Cz is kept generally constant across a stage, and Cz by U is called the flow coefficient phi. After derive the expression of blade loading capacity, I have stated here the pressure distribution around a turbine blade with the help of two figures, figure 3 and figure 4. Figure 3 and 4 illustrates the schematic of flow within the blade passage and the pressure distributions over the blade surfaces. Please note in the figure 4, I have indicated here the X chord of the blade, pitch, and the throat. Throat is the location of minimum cross-sectional area of the blade passage, and one surface of a turbine blade is indicated as suction surface and one surface is indicated as pressure surface. Now look along the pressure surface. In the first half, the flow or the pressure remains almost invariant. Then the flow will accelerate and the pressure will drop at a very high rate. While on the suction surface, The flow will accelerate in the beginning, thereby the pressure will drop, and after a certain point, particularly after the third, the flow will diffuse or flow will decelerate against an adverse pressure gradient. So this region, where the region of diffusions is very important or very sensitive, even for a low pressure turbine, for high diffusion leads to flow separations. What explained earlier, I have summarized here stating that the flow locally accelerates on the first half of the suction surface of a turbine blade, while it decelerates in the second half against an adverse pressure gradient. Thus, a zone of diffusion appears in the second half, depending on turning of flow within the blade passage. Furthermore, the boundary layer could grow rapidly or even separate in the zone of diffusion, affecting adversely the efficiency of a turbine stage. Different design groups have their own rules learned through experience and testings for the amount of diffusion which is permeable on the suction surface, particularly for highly loaded blades. Overall, I can say that the boundary layer on the blade surfaces is not very sensitive in case of a turbine, and the designer here has more freedom in distributing the total stage pressure between the rotor and the stator. In this lecture, I have discussed about two-dimensional pitch line design and derived the expression for blade loading capacity. Furthermore, I have indicated that boundary layer growth on the blade surface of a turbine stage would be much less as compared to compression, as the boundary layer grows against favorable pressure gradients. Thus, the efficiency is expected here higher than that of the compressor. However, on the suction surface, in the second half, a zone of diffusions appear where the boundary layer grow against adverse pressure gradients for a highly loaded blade. Thus, while designing a highly loaded blade, caution to be taken so that boundary layer does not separate in the second half of a turbine blade, because the separations adversely affect the efficiency of the stage. Thank you for listening.